We're moving on to AP Physics experiments. This is video number 4. We're going to do waves and a little bit on circuits here. Okay, so let's get started. This is a wavelength here, again, from crest to crest. This is a slinky going up and down like this. This is a transverse wave, and of course this one's a longitudinal wave here. Okay, so we have a compression, an extension, and a compression. So we measure the wavelength by 2 expansions we call rarefractions, or you can measure it between 2 compressions. The wavelength of a transverse wave, of course, is between one crest or one trough to another trough, or one crest to another crest. Okay, well, our equation for this is velocity is equal to the square root of force tension divided by mu. Mu is the linear density. So if I graph velocity versus force tension, I would not get a straight line, so I got to make a square root here. And that'll give me some kind of a straight line, probably starting close to 0. So if I look at this, velocity then is equal to, I got to do 1 over the square root of mu multiplied by the square root of force tension. Again, I'm in V, okay, is equal to mx. X this time is the square root of force tension. M is 1 over the square root of mu. So if I take the slope of that, I would then get 1 over, that equals 1 over the square root of mu. Now remember, the velocity of sound in air has a similar equation, except now it's equal to bulk modulus, okay, divided by density. This one's linear density, that's just density. So depending on what you want to graph there, that one's more challenging to graph, of course. More challenging to get results for. Now let's talk about the speed of a wave. Now we can look at the speed of a wave. Let's look at the transverse wave. We have a y velocity. I'll just do 2 small graphs here. You can have a y versus time. Okay, and then there's also an x versus time. There's 2 things going on here. We have this thing oscillating up and down, but also moving in this way. So just remember to keep those 2 separately. As this thing goes up and down, this of course defines the amplitude. Okay, so if I want the velocity in the y direction, I could take the amplitude, okay, divided by the period divided by 4, right? Because if it goes up in amplitude, remember, let's draw kind of like a dashed line through here to represent the equilibrium line here. My amplitude is up there. So if I go from up there up to there, and then back down and up here, if I just trace this wave here, the amplitude is only 1/4 of the time. If I want to get velocity in the x direction, that's going to be equal to the wavelength, okay, divided by time. So I'll go lambda divided by time. Because remember, it's propagating this way as well. So just a reminder about that. And it's nice to approximate these kind of waves as a transverse wave. It kind of helps us understand that, at least for me anyway. So the compression here is going to be a trough here, or the expansion or the rarefaction will be a trough here, and the compression, okay, will be a crest here. So it's really useful to take these waves and make it look like this to help us be able to do that. Okay, now what about a rope? So if we have a rope fixed at one end, the wave pulse comes in like this, hits, and it will be inverted on the way back. What if it's loose on one end, so this is able to vibrate up and down very easily? Well, the wave will come in, it'll reflect, and it'll come back up. Okay, it does not invert downwards, because this was able to go up and down. So that's pretty characteristic of how waves reflect. And again, that's just a reflection off of a surface. In AP Physics 2, we get into more detail as to why that happens. At any rate, if you create interference patterns, you can get what looks like a standing wave here. So this wave here may be vibrating back and forth. A lot of times we show this with 2 boundary positions here, and then let's say we got something going like this, back and forth like this. And this is just a regular guitar string vibrating back and forth like this. It looks like a standing wave because it's not moving anywhere. So, but it is oscillating up and down. We can look at the velocity in the y direction for this and see how much it goes up and down. So one time it goes up like that, remember, is 1/4 of a period. So we can definitely look at velocity in the y direction as this thing oscillates back and forth. And remember, the second harmonic would have a node in here, and the wave pattern would change like this. I'm going to just try to approximate that inside there for you. And then there would be a third harmonic, fourth harmonic, etc., etc. Okay, and our harmonic pattern, speaking of which, let's go to that right now. For a string, we have velocity is equal to nv over 2L. And n equals 1, 2, 3, etc., etc. That's the same thing as just a hollow tube. Velocity for when you close off one end equals nv over 4L. And n equals 1, 3, 5, etc. So this one here also works for springs and also just strings. So let's go back to that. Let's draw the first harmonic in there. There you go. And of course this is a node, and then there's an antinode, and that's a node, which is half of a wave. And then of course this one here is an antinode, node, antinode, which is also half a wave. So that's why you put 1 in here to get half of a wave. And when you close off one end, it's antinode and then node. Okay, which is only 1/4 of a wave. So you can use these in order to, maybe get the speed of a wave or get the speed of sound. And we did this one in class. If I vary frequency, okay, and actually I just saw something I want to correct really fast here. This is supposed to be frequency over here. So let's get that fixed really quickly. So it's frequency equals nv over 2L, and this is frequency equals nv over 2L. These are velocities, or this is 4L. So these are velocities here. The frequency is on the left and velocity is on the right. So at any rate, we can use these equations in order to determine the speed of the waves. Okay, if I did, for instance, this one, let's do the graduated cylinder, close that one in here. So if I did frequency here, versus length, that's not going to work. I need to graph it versus 1 over L, because L is on the bottom here. Okay, and I will get some kind of a straight line. Okay, and we'll just approximate a straight line here somewhere. Okay, so let's look at this equation. So if I rearrange this equation, it's going to be frequency is equal to the n. Let's choose n equal 1 every time when I do this experiment. So that 1 would be the fundamental frequency of this. I'm not going to have n, 2, and 3. So I'm just varying frequency when I do this experiment, but I keep 1 for n each time. So that's then going to equal the speed over 4, and I'll put that in parentheses, and then I'll have 1 over L here. So what equation do we have? Again, I've got y is equal to mx. X this time is 1 over L, because that's where my equation is. L is on the bottom over here. And my slope is the constant in front. Okay, so just v over 4. So the speed of sound divided by 4. And if I did it for strings, I would be doing the speed of the waves on the string divided by 2. Or if I did hollow tubes open on both ends, then it's the speed of sound divided by 2 again. So hopefully that makes pretty good sense there for you. So we can use harmonics to get the speed of the waves just by making those appropriate graphs. Remember, it is frequency equals nv over 2L, and frequency is nv over 4L. Hopefully that makes good sense. Now, what about some circuits? Let's do something pretty simple here. Okay, we talked about internal resistance of a battery already. So let's say I have a battery, and we're going to use this little thing here to represent the resistance of the battery. Okay, so we're going to call this R sub B. This, of course, is the battery here, going around here. Okay, and let's put a load resistor in here. We'll call that R sub L, and that's just a resistor, so the circuit isn't just short-circuited. Okay, and then let's put an ammeter in here. So I just want to kind of remind you about how we do circuits here. Ammeters go directly into the circuits, and voltmeters go outside the circuit and are parallel to the resistors here. Okay, remember, for an ammeter, I'll just use an A like this. This is our symbol for ammeter. The resistance is very low. We don't want to disturb the resistance of the whole circuit, disturb the current. So remember, when adding an ammeter to the circuit, you will create a little extra resistance in the circuit, so the current that you're measuring is actually lower than it actually is. But the voltmeter, since we're in parallel, we want resistance to be very high. The reason is we don't want to draw off much current to measure the voltage. But again, remember, we are disturbing the circuit. You are drawing some current off of the circuit. And then how does it work? Well, since the voltage meter is parallel to the resistor, whatever voltage the voltage meter reads must be the voltage on the resistor. But again, remember, in true experiments, we definitely have disturbed the circuit. So make sure you're able to handle that. Let's call this one here volts of the battery. So if I want to find the internal resistance of the battery here, we have some pretty good information here that we can use. Let's use Kirchhoff's rules for this. Okay, remember that Kirchhoff's rule states that the sum of all volts in any loop must equal 0. Okay, so I'm going to say, well, this is a voltage rise. Now let's put our plus minus on everything here. There's a plus on this and a minus on this one. So I'm experiencing a voltage rise here if I do a clockwise loop here, because I see a negative to a positive. So I have volts of the battery. Okay, and I'm going to have a voltage drop across RB. So that's going to be I times RB. Okay, and I know I because I measured I right there. Okay, and then I'm going to go minus the volts across the load resistor, and that would equal 0. So if I measure the current there, and I measure the volts there, I know the voltage of my battery, getting the resistance of the battery is very easy to do. Okay, and just one last thing to remind us about circuits. Remember the Kirchhoff's current loop or current juncture idea? So if I have a circuit that goes something like this, and it goes around like this, I'll just do something quite simple here. So if I just have a branch coming off like this, and I've got some current 1 coming in here, and I've got a current going this way and a current going this way. Let's call this one current 2, and this one current 3. According to Kirchhoff's rules, that I1 coming in must equal I2 plus I3. So think of Kirchhoff's rules just as conservation energy as applied to circuits. Okay, and that's it for this movie. One more movie coming up.